Welcome to lecture 2. So I looked over how much material I have, and it's about 5 hours worth. So I'm going to talk really, really fast. That's a joke. We'll get as far as we can. Hopefully you'll pick up 2 really, really important sort of mathematical techniques. So let me start with an equation I wrote down yesterday. So this is a leaky integrating fire neuron. So voltage on neuron I minus leak reversible potential. So basically what this says, if neurons are left to their own devices, they'll relax back to some memory potential. This is about 10 milliseconds. And their input is sum on J of Wij, Gj of T. So these are spikes from other neurons. And then, and this is, of course, the connection strength, the weights. And we're going to add to this, external input. So let's call it II, external. And these, of course, are also spike trains. And of course, this is a leaky integrating fire neuron, so the memory goes above some threshold that emits a spike. Okay? So this is not a bad model of the brain. It's got spikes. It's got sort of characteristic of neurons, which they have a really short temporal memory. Neurons only remember things about 10 and 20 milliseconds back. They try to decay to some resting potential, which is about minus 50 millivolts. And then so V greater than equal to, say, this is minus 65. It sits here around minus 65 millivolts, and when V greater than equal to minus 50 millivolts, emit a spike and reset to minus 50. Sorry, to minus 65. And remember, Gj of T looks like this. So these are spike times. This is time. These are spike times. And every time a neuron spikes, this jumps up by a little bit. Jumps up, some shape or other. So on. Okay. So this is a neural network. This is kind of what we know about them. And it would be really nice to know their input-output function. So it'd be really nice to know if, I can tell you something about the input, you'll tell me something about the outputs. And the idea then, since it's, if all goes well, neurons are divided into many networks, or sort of our view of the brain is that there are lots of different areas. And if you can understand something qualitatively or quantitatively about the input-output function of these areas, we would know a lot. We still would have no idea how it worked. But remember, so yesterday, when I talked 2 days ago, I said networks aren't really human understandable. That's probably true, but we can understand things about them. Okay, we can't understand a specific transformation they could do, but we can understand kind of how they work. So this is in the category of gain insight into networks of spiky neurons. It's also, we would love to get rid of spikes. So if you ever done analysis with spikes, it's a complete pain in the ass, just because they don't happen very often. So they're highly nonlinear, very noisy. If we could replace spiking networks by rate neurons, for which we have analog rates, at least from an analytic point of view, that would be really, really nice. Okay. So our goal, which we're not going to get to today, is, so input, this is II external, which consists of lots of different neurons. All these are all spiky neurons, right? We have in here some recurrent network. These connect to these neurons. And then these, basically, there's some output neurons. But in fact, we're going to ask, what's the activity on every neuron? on neurons in the network. Okay. So you'll notice that the key hard term in here is this one. So I'm going to spend a fair amount of time talking about that. In fact, although this is what I want to do, I'm going to mainly ignore external input. And the reason for that is we want to understand how external input affects the network. We need to understand how the network works without external input. If I were designing a brain, I would basically, so go back to here, I would design it so that when there's no input, the network is just dead quiet. Turns out the brain had other ideas. When there's no input, the network is firing away. Sorry about the call. So we really want to understand this activity of this network in the absence of input. Okay, so that's the goal for today. Was there a question? Okay, and again, what we're going to focus on is for at least for a while, is this term here, the synaptic input. And the first thing I'm going to do is change that a little bit. I'm going to write it, so we have this term, this is recurrent connectivity. So I wrote this as a sum on J of Wij Gj of T. I'm going to assume there are n neurons and they're all tall connected. And I divide this by root n, and you'll see why in just a second. And I'm going to make this term completely random. So Wij is just pulled from some probability distribution independently IID. So Wij, some distribution P of Wij. It's just some distribution P of W. Okay. Now, totally random networks aren't that interesting, you would think. Turns out they're surprisingly hard to analyze. But we ultimately are interested in structure. In fact, if I had an extra 4 hours, I would talk about structure. But if we think about what structure looks like, it turns out it has a form like this: 1 over n, the sum on mu of ai mu b. Well, we think it has a form kind of like this. Not sure how much you've heard about neural networks, especially recurrent networks. So P is typically much less than n. And so why this particular form? Okay, so it has to do with so the idea is that if Gj is proportional to Bi for some mu, then this last term, 1 over n, the sum on mu ai mu bi mu, we'll put in actually a j here. Sorry. B j nu. So bi mu sum on n is also a sum on j. Sum on j of bi mu b bj nu. This is the mu equals nu term, the 1 over n. So that's order 1. Let me talk about orders all the time. So n is large because it's a neural network, n is much greater than 1. So we really care about how things scale with n. Okay, so when G is lined up with one of these vectors, this term is big, right? And the whole term, so we can write this as 1 over sum on mu not equal to nu of ai mu 1 over n sum on j b j mu b j nu plus ai nu 1 over n sum on j b j nu. And this quantity here is order 1. Okay, so quiz number 1. How big if bj nu and so this term, the mu term and the nu term are uncorrelated, how big is this term? Anybody know? Anybody want to guess? No takers.
There's a taker. So the question is, why does the scale as like 1 over n instead of just 1 over square root of n, or what?
Well, so the g's, I mean, it's a little, so I haven't given you all the information. So the b's are zero mean. So we're adding together a bunch of, so we're adding together n uncorrelated zero mean random variables. Do you know what we get?
Yeah.
Yeah?
Yeah, I got it, but I have no clue.
Okay, it's 1 over root n.
Yeah.
I actually spent a lot of time on the scaling. And that's basically, well, I'll come back to that. That's 1 over root n. This is order 1. And this term is actually, so I'm actually going to show that on the next page. So if you have, this is something you guys need to know inside and out. If you have 1 over n, the sum on I of squiggle I. So squiggle I, the mean value of squiggle I is equal to 0. These are zero mean random variables. Squiggle I, squiggle j is equal to sigma squared delta ij. So these are uncorrelated zero mean random variables, about as simple as you can get. On average, 1 over n, the sum on I of squiggle I equals 1 over n, sum on I, average of squiggle I equals 0. Okay, this is just a central limit theorem stuff, although we don't really care about the fact that it's Gaussian. It's 0 on average. What about when we square it? So 1 over n, the sum on I of squiggle I squared is 1 over n squared, the sum on ij of average of squiggle I squiggle j. And if I is not equal to j, you get nothing, right? So this is 1 over n squared, the sum on I of average of squiggle I squared. So every one of these terms is sigma squared, and there are n of them, so we just get sigma squared over n. Okay. So this quantity here, give it a big X. The mean value of X is 0, and its variance scale is 1 over n. So X equals 1 over n, the sum on I of squiggle I, equals basically sigma over root n times some zero mean unit variance. And it turns out to be Gaussian. Okay. So the average of n uncorrelated zero mean random variables is order root n. Okay, I want that to be burned into your memories because it's critical for what I'm going to say. Okay. So let's go back to this. So this term was 1 over n. These are 1 over n times random variables. Get 1 over root n. So we can kind of ignore this, right? When g is proportional to b, we get something out, right? That's sort of structured and correlated. What about over here? We're adding up, if g is, assuming w is random, no matter what G you put here, you're adding up n random variables, but you're dividing by root n instead of n. So no matter what, this term is going to be, oops. This term is going to be order 1. Okay, and it's going to be basically noise. So it's kind of interesting. If you have random connectivity, which the brain apparently has, it's basically always going to be kind of big, assuming that W is zero mean. We'll get to the non-zero mean case in a while. And it interacts with, this is a structured term. This is a part of the connectivity that actually does something useful. And that structured part is going to interact strongly with the noise. Okay. If, on the other hand, so this is take-home lesson number 1. We assume that there's some random component to your connectivity in your brain, just because of biology, there's always randomness. The structured part looks something like this. We don't know for sure, but it's a reasonable guess. And what the structured part does is pick out particular inputs and in some sense amplifies them and shuts off everything else. Okay? And so there's one more thing we need to know. So if GJ is not proportional to BJ nu, for any nu, then we can ignore this term. That allows us to ignore structure. Okay. So, and what we're going to do as a first pass is assume that you have some network with some structure in it maybe, but the structure is really not having any effect because none of the inputs are really ever lined up. Okay, so we're in this regime. We have a structured part to our network, but the structured part is not being used. So we're just going to consider what seems like a sort of a strangely bizarre, easy problem, is we're going to get rid of that. Okay. And this is pretty important. So a lot just went on. The logic of getting rid of that is that if GJ is not it's not lined up to take advantage of this particular B, it doesn't play a big role. It doesn't play a big role because of this fact, that uncorrelated random variables, average uncorrelated random variables is small. Okay. And so what we're going to do is consider just this term. So our goal now is to basically, we're going to consider a network that looks like this. Tau dvi dt equals minus. Doesn't really matter what we put here. E leak plus the sum on j 1 over n root n. You'll see why we put a root n there in a while. Wij g of t. Okay, and we're going to, at the back of our mind, we think of structured connectivity and external input. But we'll ignore for now. And like I said, if I had 5 more hours, I would tell you about them. Okay, we're just going to consider this network. So I've been talking about zero mean variables. In fact, Wij is, so we know from Wij is sort of either positive mean for excitatory neurons and negative mean for inhibitory neurons. But we'll forget about excitatory and inhibitory right now. We'll just assume that Wij has some non-zero mean. So Wij equals before I do that, I'm going to do something else. Well, Wij equals no, we're not going to do that yet. Okay, the first thing we're going to do is get rid of time. So GJ, so we can think of the firing rate of neuron J is the time average of GJ of T. And this equals in the long time limit as T goes to infinity. The integral 0 to T dt GJ of T. Sorry. So here's what we're gonna do. We're gonna actually, we'll take GJ of T and replace it by its time average over time, plus fluctuations around those time averages. Okay. And it's we're gonna choose GJ of T. So this is the definition of the time average. I'll take limit as T is very large. And remember, the sum on K of GJ of T minus TJK. So this is K spike on neuron J. And GJ, I'm going to call this GJ. And GJ looks like this. So this is T equals 0. It goes up and it comes down. And we're going to define it so that area equals 1. In that case, this thing just counts spikes. Once we do the integral, this is just N J of T. Capital T equals number presynaptic spikes time T. So we have average value of GJ bar is equal to NJ of T over T. And that by definition is firing rate. Okay. So we've basically chosen normalization so that this term here is, this is just nu J. Okay. So we have tau dvi dt equals minus vi minus e leak plus the sum on J 1 over root n wij nu J of T plus 1 over root n sum on J wij delta GJ of T. So these are fluctuations, temporal fluctuations. Okay, so what's this mean as far as the neuron's firing goes? If we plot voltage on this axis, well, let's put this is minus 50, and this is minus 65. So the synaptic drive is this term. This is, our model firing rates are fixed. So this term for neuron I, this is just a number, okay? And it's going to provide constant drive. If you combine it with this thing, it's going to give you some memory potential. And so that number here is going to give you some mean. There's going to be some mean value for neuron I that's determined by the firing rates of the presynaptic cells and the weights. The fluctuations, on the other hand, this term is going to cause fluctuations. Whenever the neuron hits there, remember it fires and comes back and then fluctuates again. Okay? And the firing rate of neuron I, nu I equals some function of this gap, the function of this gap, which means it's a function of 1 over root n, sum on j of w I j nu j. Okay. Now this is, we'll see later on if we have time. This is a little bit of a cheat, right? Because we're acting like these fluctuations here are sort of fixed, independent of everything else. This actually turns out not to be such a bad approximation. It kind of matters if there are temporal correlations in the spikes. You might have heard about that in other lectures. If not, but this is sort of an approximation we're going to make. So this is nice in a couple ways. One is we can analyze this equation, and the other is we've gotten rid of spikes. Basically say, look at neurons, just they fluctuate, these fluctuations cause spikes, and all we care about is the firing rate. And our goal now is, given what our goal now for the rest of the however long I have, is to compute the firing rate of all the neurons given the weights. Okay? Or given, so that would be one thing we might want to calculate. And what we're going to do instead is going to compute the distribution of firing rates given the statistics of the weights. Okay. Now this seems like a hard problem, but we're going to take n goes to infinity. And as we all know, whenever n goes to infinity, life is much, much easier. Question? Okay. So I'm going to start with a warm-up problem. So in real life, this is complicated by the fact that neurons are both excitatory and inhibitory. But I'm going to start off with a warm-up problem, which neurons are all inhibitory. I think I saw this problem work for the first time by John Hertz many, many years ago. And what we're going to write is that a nu I equals some function. Actually, I'm going to use some function phi of root n mu 0 minus or plus 1 over root n, the sum on j of w I j nu j. This problem we're going to solve. So wij equals minus w bar, some constant, plus sigma delta w ij, where this is, actually I'm going to write it as delta w ij, where these are uncorrelated random variables. So they're uncorrelated. They're just pulled from some distribution, and the average they're 0, and the variance of delta wij equals sigma squared. Okay, this is all we know. So the first thing we're going to do is so 1 over root n, sum on j of wij nu j equals 1 over root n, the sum on j of two terms, minus w bar, nu j, and then plus 1 over root n, the sum on j of delta wij, uj. And the first term is equal, so minus w bar comes out. There are n terms in this sum, but we only divide by root n. So we get a minus root n w bar nu bar. So nu bar is 1 over n, sum on I of nu I. Okay. So that's first term is kind of big, and this is why we had to have a root n mu here to cancel things out. What about the second term? So the second term is zero mean, but it's got a non-zero variance with respect to the index I. So for every I, we're going to get a different number. And we want to know the variance of this thing. So we're going to say, what we're going to say is 1 over root n, the sum on j of delta w I j nu j. I'm going to call this something called squiggle I. Squiggle I is a zero mean random variable, but every time we put in a different I, we're going to get a different number. So we're going to compute the variance of squiggle as 1 over n, the sum on I of squiggle I squared. Okay. Any guesses as to how it scales with n? If I could have a show of hands. Okay, so it's sort of, it's order 1, order n, order 1 over root n. Anybody venture a guess?
Should it be 1?
Well, it should be order 1, right? We're adding up n random variables. The average of n random variables, remember, scales is 1 over root n. Well, the average of n random variable scales is 1 over root n, but we have only 1 over root n in front. Okay, so it's exactly right. So this is equal to 1 over n, the sum on I, of the sum on j, of delta w I j nu j squared. So sum on j, we can just sum over j and j prime. So we have the sum on j and j prime, nu j prime, and then 1 over n, the sum on I, delta w I j, delta w I j prime. Okay, and this quantity here is equal to sigma squared if I equals j. And 0 if I is not equal to j on average. And we forgot a 1 over n that goes in, 1 over root n goes in here. So we have 1 over root n here. Sorry. So we have equals 1 over. But this 1 over root n, this term here got squared. Okay. And so this quantity here is basically we only keep the j equal j prime, j not equal to j prime. So this sum here, we only keep the sum j equals j prime. If we do that, we get nu j squared. So this quantity here is equal to, on average, sigma squared nu squared. Okay. So what's that mean? So squiggle I, it's a zero mean random variable. But for the central limit theorem, squiggle I is approximately Gaussian. There are small issues because of correlations that squeak in, but squiggle I or P of squiggle I, e to the minus squiggle I squared over 2 sigma squared nu squared over the square root of 2 pi sigma squared nu squared. Okay, so this quantity here is a zero mean Gaussian random variable. So if it is used to this 0, this is 0. Zero mean invariance is sigma squared, which is variance of the weights, times the second moment of the firing rate. Okay? So that's nice, but why do we care? So we care for the following reason. We have this equation, nu I equals some function of root n mu 0. If you remember, the mean value of this quantity was minus root n w bar nu bar, okay? And this is just a Gaussian random variable with this standard deviation. So we're going to write this as minus root n w bar nu bar. And then this is the important part. We're going to write this as sigma, the square root of nu squared, times zi, where this thing is normal. It's a normal 0, 1. It's unit variance, zero mean unit variance Gaussian random variable. So why is this nice? Because we can compute average value of nu. So the left-hand side, so what we've done is completely ignore correlations. So the idea here, so we're pretending like zi is independent of nu I. And the reason we can do that, the deep reason, to this day I don't know quite what it is. The deep reason is because when we multiply by this random matrix, it completely scrambles any information about nu j. Okay, it doesn't completely scramble it, but it pretty much, for all intents and purposes, it scrambles it. So this quantity here is independent of this quantity here. Okay, this is a insanely non-trivial result, which works really well in simulations. I've never checked exactly why it's true, but it's kind of reasonable. So what's that mean? That means nu I bar, so the right-hand side depends on the first and second moments of the firing rates, nu and nu squared, right? I'm using a mixed up notation. So the average value of nu to the power k is 1 over n, the sum on I, phi of root n u0 minus w bar nu bar plus sigma, the square root, if I should use better notation, times zi. Okay? And zi is sampled from a normal distribution. So what does that mean? That means in limit of large n, we can do an integral. Integral dz e to the minus z squared over 2 over root 2 pi, phi to the power k, root n u0 minus w bar u bar plus sigma, the square root of u squared z. And for consistency, I should probably write this as u. Okay, so these quantities here, so this is nice. We have to do two integrals. The integral for k equals 1, and that'll give us For k equals 1, that'll give us nu bar. For k equals 2, that'll give us nu squared bar. Two equations, two unknowns. And once we know nu bar, nu squared bar, we can sample from this to get the whole distribution of fine rates. Okay? So this is a kind of a mind-bogglingly beautiful result. I can say that because I didn't think of that myself. I'll give you guys a whole long list of references that goes back a long way, including John Hertz's book, which is, if it's still in print, it's a great book. So this was really, really fast. I'm going to give you guys an assignment. I want you to spend about 5 or maybe, we'll see how long it takes, 5 or maybe 10 minutes working this out. I'm going to consider a really simple case, and it's kind of surprising. So phi of all this cool stuff equals a Heaviside step function. Phi of x equals theta of x equals 1 if x is greater than 0 and 0 if x. Okay. So the nice thing about this is that nu squared okay. So I want you to compute. We're going to use exactly this model. We have a mu naught. This is exactly our model. W bar or sigma, those are the parameters of the model. I want you to compute the average firing rate as a function of those parameters. So I'm going to let you guys scribble on a piece of paper for a little while. Let's just go 5 minutes. It's sort of worth spending time on. Once you've done it once, it's going to be a whole lot easier. Okay, so I'll sort of stop babbling and let you guys think for a little bit. Okay, I can kind of see you guys. Show of hands, how many people think they got it?
Is it like 1 over square root of 2?
I actually don't know, but I'll work it out. In fact, when it comes down to it, all we want to do is this integral. But because nu squared bar equals nu bar, right? Because x squared, and if basically nu squared equals nu, because it's a step function, we do the integral with, we just replace this with nu bar, which we only now have one order parameter, the mean firing rate. And so our equation becomes nu bar equals integral dz e to the minus z squared over 2 over root 2 pi times theta step function of root n u0 minus w bar sigma square root of nu bar z. And basically what this means is we integrate over z such that this whole term is greater than 0. Okay, so sigma the square root of nu z must be greater than or equal to, must be greater than root n w bar nu bar minus mu naught. Okay, or z is greater than root n over sigma. So w bar, the square root of nu bar minus mu naught over the square root of nu bar. Okay, so the integral goes from, so the integral goes from this point. So given that, so nu equals the integral from z naught to infinity dz e to the minus z squared over 2 of just 1, right? Theta is 1. So this is an error function. It's basically phi of, it doesn't matter, minus z naught. Okay. Phi is a cumulative normal distribution. But this one, it's sort of easy, right? So nu equals phi of minus z naught. And for z naught, we just stuck this in here. So we still have kind of a hard problem. We have to solve for the self-consistently, but it's not really that hard to do. You should definitely, I'll give you these notes, you should definitely work it out in your own time. It's kind of interesting. There's one more thing I want to point out. Okay, so was that pretty much okay with just the observation? This is an especially simple case when we only have to compute one integral instead of two, and just notice that the range of z is determined by what happens over here. Okay, and you get a Gaussian integral, but that's a little bit of a detail. So there's one thing really, really important to notice about this. So if you look at, so we ended up having nu I equals phi of root n mu 0 minus w bar u bar plus sigma square root of u squared zi, where this is normal 0, 1. Okay. And then we have, let's just take nu bar. So nu bar equals integral dz e to the minus z squared over 2 over 2 pi times all this. Okay. So this is a convolution. Okay. We're just smearing this. If phi, we'll even sort of take an extreme case, one we took before. Phi looks like, sort of like this. After the convolution, so this quantity here, this integral, all it does is smear this out a little bit. Okay, so this is integral dz e to the minus z squared over 2 over root 2 pi of dot, dot, dot. Okay. The amount it smears it out scales with, depends on the second moment. Okay, but the point is that a lot of our intuition is going to come from the generic shape of these gain functions. So the fact that it smears it out is kind of not a big deal. In fact, so we can sort of almost, for qualitative understanding, we're just going to throw this away. We're going to replace phi by some smoothed out version of itself and throw this away, ultimately. Okay, so let's summarize the main take-home points. First main take-home point is this: if you average some zero mean uncorrelated random variables, you end up with something whose size is 1 over root n times the Gaussian random variable. So that's something you should double check about 6 times. It's one of the most important facts in the world. The other important thing is we can basically take this quantity here, express it as just a random variable that's uncorrelated with this, which is obviously a big approximation. Okay, and it's rigorous for sparse networks. You'll actually see some, if you do simulations, you'll see some departures from the theory because of the weak correlations. But it turns out if this is random, it's a pretty good approximation. Okay, and we can use that to actually solve equations, right? We can write this down, and then we can find moments just by turning sums over I into integrals over Gaussian random variables. Okay. So if you absorbed all that, I'll be very, very, very happy. And believe me, this shows up all the time. So I only know 4 tricks as a physicist, and one of them is if I see a large sum, I pretend like it's a Gaussian random variable. It works insanely well. Okay.
Peter, now that you got here, can I ask you a question?
Sure.
So all this is kind of a mean field approximation, but
yeah,
and large. And now I know that also in practice we've done these things for a million times, and we compare with simulations, and it works well. But I always have this nightmare that for finite n, the central limit theorem has corrections, and why don't they ever show up in some? I imagine in if you look at typical systems that those effects are not relevant, but there should be individual cases of networks that you build, and these things even large, but these things blow up. Has anybody looked into that, or is there any reason why they? Are we just lucky, or?
Yeah, we're pretty lucky. So a couple things. So it turns out that it's really not n that matters, it's number of connections k. I mean, it's worse. It's really a bad situation. And k is about 1,000 in the brain. So we're talking about 1/√1000 is 1/30th. So the first observation is we're not really even the large limit.
Yeah, I mean, it's the limit of 30 to infinity.
Yeah, 30 equals infinity for large 30.
It's not.
Even when I've done simulations, even when n goes to infinity, for networks like this, you'll get really good agreement with theory. If you do excitatory and inhibitory neurons, which I'm about to talk about, even for large n, you see order 1 departures. And I think it's because it's mean field theory. This is not really Gaussian. There's some correlation floating around that we haven't dealt with.
But do you know if it's possible to do like a perturbative expansion in 1/n with the? I mean, everything you did, you could just say that when you approximated all those terms with the mean and standard deviation, you can also add the deviations from that as a function of 1/k or 1/n.
So I tried to do that once, and where it's hard is that. Let's go back to this quantity here. Okay, so our big approximation, this quantity here, our big approximation was we could use a central limit theorem. If you think about that, it's kind of insane. These firing rates are actually a function of the weights after you solve this equation, right?
Exactly.
This is fully correlated. This is insanely correlated variable. So yeah, I think
my nightmare comes from that for some reason they seem not to.
Yeah, I mean, maybe John Hertz would know more about this than I do. Partly because because you have a scrambling effect. If this is very sparse, it becomes rigorously correct, but it has to be insanely sparse. But it's really, calculating corrections, I think, would be super fun. I spent like a day or two trying it once, and I didn't get anywhere. Because you have to look at departures from Gaussianity because of correlations. And I'm sure there's a whole field of that, which I know nothing about. It also... Right.
Even there is much simpler than that, we know some tail, I mean, how basically in the central limit you converge to the, how fast you converge to the Gaussian.
Yeah, so I think that's known.
In there, you don't really need to know the correlations, but some sort of average estimate of correlations, which is...
I think you might look at moment generating functions. As John Hertz just pointed out, for sparse networks, you can do belief propagation. If it's really sparse, it's helpful because you're asking if, it's not obvious, but for really sparse, it's helpful. If it's sparse enough, you can show rigorously they're uncorrelated. And again, I think by central, you can use generating functions to look at departures from Gaussianity. But there's a worse problem on that. The worst problem, of course, is it's really number of connections, not n, and that's only about 1,000. And the other problem, if you look at it, it turns out that I'm not going to have time for this. You can use it as a homework problem. This quantity here, it's actually so you kind of want the sum on J. You kind of want this to be, well, I'll do it now. Okay, what we have, remember, is 1 over root n, the sum on J. I'm going to put Wij. And replace this by Wij nu J goes to 1 over root n. We've already seen this. So when you just average this thing, it's really, really crude. It goes to root n W bar nu bar. Okay. And root n is really root k, where k equals number connections per neuron. So it turns out what goes here? What goes here is the size of a PSP, and it's really times the membrane time constant. Membrane? That's no square root. There's a membrane time constant that goes in here. Times tau nu bar. So membrane time constant equals 0.01 seconds. So if nu bar is, let's say, 1 hertz, this quantity here is 1 over 100. Okay, and then we have a third root, and we have a root k in front, and this is 30. So our small parameter, which is supposed to be big, is 0.2. So this should really, we'd like to take the large n limit because we can make statements, strong statements. This should really be considered a really, really qualitative approximate theory. Okay. If you increase things, I think I might be missing a factor. But if you increase things to 10 hertz, then even 10 hertz, I think actually I'm missing a factor. I don't remember it being this small.
Wouldn't in the balanced state help with this somehow?
Well, the balanced state,
By reducing the effective time scale of the.
it does, but you're killed by this tau factor that sits out here. I wonder if it's root tau.
Relation time.
Yeah, so I actually should go back to that. This seems way too small. Might be a square root floating around. Yeah, so I mean, it turns out what you really want. Let me get to the EI networks, and we can come back to this a little bit. But really, you need firing rates nu greater than, for any of this to make sense, nu the greater than equal to a few hertz, at least. So at very low firing rates, this whole theory disintegrates. Okay. It's amazing how well it describes everything we see in the brain. And I think it's just a matter of, I think there's a deeper reason that nobody's actually investigated. Okay, so.
From Victoria, are you raising your hand because you have a question?
You can put it in the chat or relay it to Yasser.
Not really. Why?
Oh yeah, go ahead.
I have a raised hand.
Okay.
Oh, sorry. That's my mistake.
Okay. Okay, we're running out of. So let me. I'm going to save this to photos and start over because Zoom has this weird thing of only 12 whiteboards, which is bizarre. We have all this memorized. I'm going to go back and now switch to excitatory inhibitory networks. And really, it just, things are a little more complicated as far as the analysis goes, but we get something out of it. So yeah, so how much time? I started about 10 minutes late, right?
Yeah.
Okay. So I'll knock this off fairly quickly. So there are a couple of things we want to be able to derive, explain. So if you stick an electrode in the brain, you see low firing rates. Meaning on the order of, say, 5 hertz, even lower, compared to a max. Neurons can fire about 100 hertz, not for very long, but they can easily fire that. You see a broad distribution of firing rates. We want to be able to explain that. You see oscillations. So if you plot the population firing rate versus time, you often see things like this, where this is on the order of, 10 hertz plus or minus. It can be much higher, 40 hertz, 50 hertz. But oscillations are really common. And in these oscillations, E leads I. Excitatory neurons. So if this is excitatory neurons, this is the firing rate of excitatory neurons. Firing rate of inhibitory neurons follows along behind it. Okay. You see things like up-down states. Where the firing rate of the population doesn't matter E, it's going along and bam, it crashes. Stays down for a while, then comes up. Crashes, kind of irregular. And the time scale for this is in the order of 1 second. And finally, you see very irregular activity. And it turns out that low firing rates are only really understood recently, and irregular activity even more recently. In the 90s by a famous set of papers by Carl van Vriesek and Hans Samplitsky, and I'll give you those references. Okay, so these are the things we want to explain, and we want to explain it. And we're going to explain it, as Yasha pointed out, very, very approximately by making some insanely bad-looking approximations. We assume n goes to infinity when it doesn't. All sorts of reasons that shouldn't happen. But this is things that physicists are best at. Physicists are best at making stupid approximations that give you a lot of insight. And that's what we're going to do. Okay. So we're going to start with the problem with excitatory and inhibitory networks is really almost one of notation. So we have nu I. We now have excitatory and inhibitory neurons. So it just becomes a mess. So phi E, our gain function, of the sum on J of W, E, I, J. And we'll pretend like there are excitatory and inhibitory neurons, even though they have different numbers. But it doesn't really matter that much. Minus 1 over root n, sum on J of W, E, I, J, nu I, J. We also have some external input, which is going to have to scale as H. It's our external input. Eventually we'll give this temporal dynamics, but for now we won't. So nu I equals phi I. And the only thing that happens is this becomes WIE. This becomes WII. Otherwise, everything else is the same. Okay. So we're going to do, because we're now experts in suns, and so WE, all these weights has non-zero means. So we'll write W QR IJ equals W bar QR plus delta W QR IJ. QR equals E or I. And we're going to say this has variance sigma squared QR. So variance Okay, remember that's all we need. So we'll take one of these variables, 1 over root n, the sum on J of W, Q, R, I, J, nu Q, J. And we're going to let this go from our from analysis before of root n, W bar Q R, nu bar R, plus the square root of sigma squared QR, nu squared R, times Z QR, and this is normal 0, 1. Okay. So every one of these has a mean, which is root n, which is really the square number of connections. So the square number of connections is on the right of it. All it does is give you more algebra without really adding much. And so now we can write our equations as nu EI equals phi E of root n W bar, oops, actually I can write a Q there. Terms of type Q, W, Q, R, nu, R bar, minus W, sorry, W, Q, E, nu, E bar, minus W, Q, I, R, nu, I bar. Then we have plus Gaussian random variable. We have 2 Gaussian random variables, one from QE and one from QI, but since they're Gaussian, we can combine them. And we can write the square root of sigma squared QE nu E squared plus sigma squared QI nu I squared times Z Q I. And then we have plus H plus root n plus root n H E H Q I. Okay. So we have what we had before, except now we have 2 terms, which is good. Because the mean excitatory and the mean inhibitory drive in this model is large. It's got a root n in front of it. And the fluctuations are order 1. Okay. So these terms can be used to balance everything. And all this does is smear out the gain function. It takes phi E, or actually it should be phi Q, and I've erased my picture, but if phi Q looks like this, after taking into account this term here, goes like that. Okay. Actually, I may be getting ahead of myself. So keep this in mind. So I might be getting ahead of myself. Okay. So there are a couple observations here that are sort of important. So we'll ignore the external input from now. We'll pretend like, for instance, let's actually make that independent of I, so it doesn't cause any problems. Okay, it's just some constant external input. So where do we get our fluctuations? So if this term were small, all the firing weights would have the same size. Okay, so the root n here doesn't really matter because this is going to cancel that, right? We could have made this bigger but that would have made this bigger too, or we could have made this small and that would have made this smaller, okay? If we make this small by let's say, dividing all the weights by root n, this term becomes really small and every neuron has the same firing rates. Okay? It's kind of important point. This term here governs the spread in firing rates. And the reason we have a broad distribution of firing rates is because the weights have just the right size, right? We could still adjust, we could still adjust this. There's nothing, this sigma can be anything we want, right? But the variance of the weights is just the right size, gives a nice broad spread in distribution firing rates. It's not too small. If it were too small, all of neurons would fire at the same rate. If it were too big, they would basically either be not firing at all or firing at a really high rate, okay? So this is kind of nice. In some sense, this very simple theory explains the broad distribution of firing rates, okay? So as usual, that's kind of important. As usual, we want to compute our order parameters, the average firing rates and the second moments. That gives us 4 equations, 4 unknowns. Okay, but let's be a little bit sloppy and say we can solve for the second moments in terms of the first. So this is fixed, and now let's write down equations for the first moments, and we have nu e or nu q bar equals. Remember, it's 1 over n, the sum on I of a bunch of stuff. And that's going to be replaced by an integral. Phi q of root n. So w q e bar, nu e bar minus w q I bar, nu I bar. Plus some giant square root times z, actually, plus external input, HQ, and they have such giant square roots of a bunch of stuff, times z, and then, oops, e to minus z squared over 2 over root 2 pi. Again, this is just a convolution. So basically what this convolution does is smear out our gain function. Takes us from the raw gain function here. We have a raw gain function here before we start, and this convolution's integral smears it out. Okay? So we can just forget about it and write, just to get an understanding, nu q bar equals some smoothed out gain function, which I'll call phi q tilde of root n w bar qe nu e bar minus w bar. Actually, I'm going to write down both equations now. Nu e bar, oops, w e ei nu I bar plus h e, and nu I bar equals phi tilde of root n w I e bar nu I bar minus w h I. So these are our mean field equilibrium equations. And the derivation was about as sloppy as you can get, which is kind of what you want, right? You want to get the biggest bang for your buck. And you can do that if you make radical approximations, and you got to kind of cross your fingers, because you don't really know if they're going to work until you've done simulations and you've played around a lot. You'd like to be more rigorous, but some things are hard. Okay, so I'm pretty much out of time. I'm going to leave it as a homework problem. So first of all, this is an equilibrium equation, right? What happens if you start off with these firing rates way too high? Then this is going to go up. So we could just tack on some dynamics, tau E, TDE, subtract nu EI here, tau I, D, dt minus nu I. When we do that and go back here, we get the same thing. Tau E, d dt, and tau I, d dt minus nu E. Okay. So these are dynamical equations now for the excitatory and inhibitory firing, right? And so it takes kind of a long time. And so basically you can do in 2D, you can do null line analysis. And when you do, you get the famous Wilson and Cowan null lines. So Wilson, I'm guessing you guys will learn about something about this in this course. And they're super cool. On this axis, you put nu E bar. On this axis, you put, nu I bar, nu E bar. And you can plot, what you do is you plot a null line is when this quantity equals 0. You fix inhibitory firing rate, you ask, well, actually, this isn't the firing rate for which this is 0 is a curve. Okay, in 2D space. This is also a curve in 2D space, and where they intersect is where there's an equilibrium. And I'm going to draw this for root n not so big. And you get like pretty cool looking null lines. So this is somewhere like 100 hertz. And that's for the excitatory null line. The inhibitory null line looks like this. Inhibitory. Excitatory. And you can actually, the other nice thing is you can put directions. So this is d nu EDT. So it goes to the right there, it goes to the left here. This goes down and this goes up. And so this has a single fixed point right here. Depending on the parameters, that can be either stable or unstable. If it's unstable, you get oscillations. And basically the shape of these null lines, the fact that they're almost parallel, is the reason you get oscillations. Oops. And E leads I. You'll see in a second. And also the shape of these null lines tells you get no low firing rates. Okay. And the reason E leads I is because you get curves like this. So first E goes up, and then it goes down. You get oscillations like this. Okay. So I'm going to send you some. So showing this would take easily half an hour, but it's something that everybody should do once. I'll send you a bunch of references and point out which ones you can find the null lines in. It's not that hard if you've done it a million times. Otherwise, it's kind of hard. But given that it's getting late, especially for you guys, I will stop here. I'll send you these notes and tons of references.
All right. Thanks again, Peter.
Sure.
you.
Thanks,
Thanks, gang.
Peter. Thank you.
I'll see you all in Trondheim next year.
Have a nice weekend.
Yeah, you too.